In the last lecture and 2 or 3 lectures before that, we had been discussing Shor's factorization algorithm. Today we will conclude that with a discussion on how exactly this algorithm is implemented, as we have realized that the crux of the algorithm lies in finding the period of a function. So let me quickly go through the part that we did so far in connection with that. So what we said is, given a number n, choose a number m which is smaller than n such that m is co-prime with n, that is m and n do not have any common factors. And for illustration purpose, I have chosen a small number n is equal to 55. However, the quantum computation is going to be necessary when number n is very large and is a composite product of 2 prime numbers. Now let's define a function which is given by m to the power a mod n. So a is various powers, and what we had seen is the smallest value of a, which I have denoted as p, for which m to the power p is equal to 1, all these are modulus n, this is the period of the function. And our ability to factorize a large composite number lies in our being able to find p. And as we have pointed out, that for large composite numbers, our only way is to have a quantum computer which can determine the period p. So what we said is, if this is true, then m to the power p by 2 minus 1 into m to the power p by 2 plus 1, that's equal to 0 mod n. If p is even and if m to the power p by 2 plus 1 is not a multiple of n, then we can proceed with it and the Shor's algorithm works. What we said is, in order to execute this algorithm, we choose an L which is defined by 2 to the power L lying between n square and 2n square. You can always check that it is always possible to find such a number L. For instance, for n is equal to 55, we must choose q, which is given by 2 to the power L. I think this is a 12-digit or 12-bit register that we are choosing, and q is equal to 4096. With this, we first put both these registers in null state, and then by passing the first register through a series of Hadamard gates, we get the first register in a uniform linear combination of the computational basis states. Then what we do is, we have this oracle which would calculate this function m to the power a for various values of a and store all these things in the second register, which is my target register, which was initially put to be equal to 0. We had chosen, for illustration purpose, n is equal to 55 and m is equal to 13, and we had given you a table of various powers of 13, and we had seen that in this particular instance, that number 13 has a period which is equal to 20. But we will assume this to illustrate how does one proceed with this algorithm. Our next job, if you recall, having chosen a q, which is in this case 4096, a 12 qubit register, what we do is write down the initial state first, which is written as psi 1, which is equal to 1 over square root of 4096, that is 64, and first register is now a linear combination of all the basis states, which is written 0, 1, 2, 3 up to 4095, and the second register still continues to be in state 0. The oracle computes m to the power a for various values, for example, m to the power 1, m to the power 2, etc., and puts the value in the second register. There is a slight bit of an error in the last one. It should be 13 to the power 4095 because it starts with 0 and must end in 4095, and that number happens to be 32. So this is what we have got, and at that stage we measured the second register. Now when we measured the second register, it will throw a random number. Now you remember that even though we have written from 1 till 13 to the power 4095 in the second register, what actually happens is, because of the periodicity of the function, the values keep on repeating after every 20, because period was known to be 20. So therefore, I get in the second register the values that we have listed in that table for 13. Now it is one of those values which will be randomly picked up if you measure the second register, and for our purpose we have said that suppose that second register turned out to give us 9 as the measured value. Now if the second register has 9, then the minimum value for which this is valid, as we have seen in the table, is 6. So I start with 6, then I have 26, 46, 66, etc., etc., and go on till I finish this within 4096. Now that will give us 205 possible states. So these 205 possible states start with 6, in the first register, so these numbers are 6, 26, 46, etc., etc., and the last number being 4086. So these are 205 of them. So what we said is this, that when you are measuring a particular value in the second register, the first register contains a linear combination of all those values of the computational basis for which the m to the power y, if y is the index of the first register, happens to be equal to that given k, which in this case was 9. So formally the state psi 3 was shown to be equal to 1 over square root of m. This is the number of states which give you this result, which in this case is 205, sum over d is equal to 0 to m minus 1. D is simply an index of which period, which of the, is it the first 20, second 20, third 20, etc., in which this state lies. And this then would be the first one, x0, which is 6 in this case, plus d times p and this k that we have chosen. For illustration purpose, this x0 was 6 and d is a number which goes from 0 to 204, which is 205 numbers there, and p for our calculation purpose happened to be 20, and k was chosen to be equal to 9 by saying that when we measured the second register, 9 was thrown up. At this stage, we would apply a Fourier transform on the first register. So let's look at what the Fourier transform gives. Now Fourier transform is applied on the first register, remember the first register, when you apply the Fourier transform, you have to have q number of terms. So therefore let's call it psi 4, and psi 4 is equal to 1 over square root of m, which was already there in my expression, 1 over square root of q, which comes due to the Fourier transform, sum over y equal to 0 to q minus 1, then I already had sum over d equal to 0 to m minus 1. So e to the power 2 pi I y, and this was x0 plus dp divided by q, and of course y and k. Now we would write this in a slightly modified form, and this is 1 over square root of mq sum over y e to the power 2 pi I y x0 by q. Now what I do is this sum over d, let me put it inside, d equal to 0 to m minus 1 e to the power 2 pi I y dp and yk. Let me define a quantity which is z by e to the power 2 pi I y t, so that this is now written as 1 over square root of mq sum over y e to the power 2 pi I y x0 by q, and this is sum over d equal to 0 to m minus 1 of z to the power d, where z has just been defined like this. Now let us look at what is this term z to the power d. Notice, of course, this is a geometric series with common ratio equal to z, so I can easily do this sum. So let us write down how much is d equal to 0 to m minus 1 of z to the power d, and that is equal to 1 minus z to the power m divided by 1 minus z by standard formula which you have learned from school. And in this case my z was just now defined to be equal to e to the power 2 pi I y by q and a p there. So let me correct this here. There should have been a divider by q there, which I had forgotten. Now please note that this thing z, it is unimodular because it is exponential of I times something, and so therefore I can express this sum in a slightly different way. I can pull out z to the power m by 2 and write this as z to the power minus m by 2 minus z to the power m by 2, and pull out a z to the power half from here and get this as z to the power minus half minus z to the power plus half. So when I take the modulus of such a quantity, because these are unimodular, I get 1 from here, and I am then left with this expression, and since z has this structure, I get this as equal to modulus of sine function of pi y p m by q divided by sine of pi y p by q, and of course modulus there. What does this actually show? It tells us that at that stage, if I measure the first resistor, which had a linear combination of all those states for which the value of the second resistor happened to be 9, and we had taken a Fourier transform thereof. So notice, out of these 4096 possible states in the first resistor, the those states will be projected out in a measurement which have a significant probability. Now, square of this quantity is the probability, and so the slide here shows this thing, that what is the probability. So, this is, there was that 1 over square root of mq in my definition of psi 4. So, therefore, the probability is square of this and this probability that I just now calculated, because this also has a modulus, this is also an unimodular function. So, therefore, the probability of having a particular value of y, when we measure the first register, let us say probability of a particular yi is given by 1 over mq sine square of pi yi p m by q divided by sine square of pi yi p by q. This is a function with which you have some familiarity in the past, because this is the type of function which came up in many interference related problems. In any case, this is basically sine square alpha x divided by sine square x type of function, and these functions have a peak when the argument of the denominator becomes, well, multiple of pi, because in that case both the denominator and the numerator vanishes. Now, if this is not a multiple of pi, then you can calculate, and this probability turns out to be extremely small. Now, so therefore, the significant probability out of those 4086 states that we had will appear when this yp by q, if this is an integer, then the denominator will blow up. So, this will give me significant probability of projecting a particular y. Now, we already know what these locations of these things are, because we have back calculated and know that p is equal to 205, sorry, p is equal to 20, and q, of course, we know what is it. And so, therefore, we are aware that when this function will give me that. In other words, I am looking for the condition that okay, the probability is this. Let us look at the slide there, and when this happens, this thing will approach m square, because this is sine square alpha x by sine square alpha, and when sine square alpha x by sine square x, and when x tends to 0, this has a limit alpha square. So, in this case it is m square. So, therefore, it is m square by mq. So, the probability for which yi's are most likely to come out will be given by m square by mq, which is equal to m by q. And if you put in the values of m equal to 205 divided by 4096, this works out approximately equal to 0.05, that is about 5%. So, if you make a measurement of the first register, in all likelihood you will get those values of y being projected out for which the y's are multiple of 205 or thereabouts. And as you go away from it, this you can check it very easily, as you go away from those values, the probability significantly dies down. I have taken a small calculation using these and sort of trying to find out what are the likely values. So, assuming certain number of measurements that I had made, and this I simply did by randomly picking numbers which are close to multiples of 205, few of them, because they are the ones which are likely to come out, and if you calculate the probability, the probability will show peaks like this. The 0.05 is approximately the upper limit of it. So the question now is that we, having known what the period of the function is, we could use all these arguments to determine the period. But let us look at what is it that we actually want. What we want is that this quantity yp by q should be an integer. So if I want yp by q to be an integer, I need to have a reasonably smart way of determining what should be the value of p corresponding to a given n. The q is of course known, and having known what are the values of y which are likely to be projected out when we measure the first register, how do I determine p? There is a reasonably smart and fast way of determining this, and this is known as the method of continued fraction. You must have been already familiar with what is a continued fraction in your school, but let me give you a short review of what a continued fraction is. Suppose I'll do it by giving an example. You can read up any school level book to find out what it actually is. So let me take this number 7 by 47, 17 by 47. So how do I express this as a continued fraction? So first thing is to find out its integral part, which in all our cases it will become 0, because we have said that there would be a number here and this will be the bigger number. So this is 0 plus. Now you write this as 1 over this time 47 by 17. Now this now will be 1 over, again determine the integer part, which is 2 in this case. So 2 plus 13 by 17. Repeat this, 1 over 2 plus 1 by 17 by 13. See, every time this smaller fraction you write as 1 divided by the inverting that fraction. So it is 0 plus 1 by 2 plus 1 by 1 plus 4 by 13, and that finally gives me 0 by 1 plus 1 by 1 plus 1 by 13 by 4, which is 3 plus 1 by 4. Now when I reach 1 here, my expansion in the form of continued fraction stops. And then what I do is the following. I say that this number is expressed as 0, 2, these numbers, 1, 3 and finally 4. So given this, you can immediately write down any, this is the expansion given and you know what it stood actually for. So therefore, if I have a number x whose continued fraction is given, what I do is this, I say that x is equal to some a0, a1 up to let us say am, and supposing I stop this at a0, a1 up to aj, then I will say this is jth convergent of x. So what we want now is how to express y by q as n by p. This is what you are looking for. So y by q is the rational fraction and we want to find the period. So what we do is we express y by 2 as a continued fraction and look at various convergents of it but then approximate by that fraction for which the denominator starts exceeding the original number n. So let me illustrate how it works. So we have this number. Suppose my result gave me 408. This is one of the possibilities, because 205 into 2 is 410, and supposing I got 408. So I have 408 divided by 4096. I will not repeat this calculation, but you can immediately check that this can be expressed as 1 by 10 plus 25 plus 1 by 2. So what are my various convergent? My first convergent is simply 1 by 10. Now if you look at the second convergent, this is obtained by removing this, and the second convergent will then be 25 by 251. But by this time, this has already exceeded n. So therefore, I stop at the first convergent. Since 1 by 10 is an approximation to this, it means that, and remember I am looking for an approximation which is n by t. So therefore, this number 10 must be a multiple of p, because if there is a common factor between n and p, that will cancel out. And you can immediately see the possibilities are 10, 20, etc., 30, 40, 50. Because after that it will become 60 and will exceed n, and you have to stop. At that stage, what you do is find out what is a to the power p. So if it is 10, I have given you already table 13 to the power p, and you will immediately see 13 to the power 20 will become 1. So this is a very fast way of finding out a period after having a measurement of the first register. With this, we conclude our discussion of Shor's algorithm, and the reason why we have spent so much of time on this particular algorithm is, as we have pointed out, this is one situation where a problem which is not solvable by the classical computers in polynomial time can be solved in a time with in time and resource, or a complexity of the order of polynomial in logarithm of the input.